is 5.4. 5.4, we're talking about the bending. Okay, when we're talking about bending, you may recall that means it's going to be the beam. We have the beam and our beam subjected to the force. Let's say this is P. You may get this reaction, and it's going to be P over half and P over half if this one is L over 2 and L over 2. Okay, this kind of test is called three-point loading test. What we like, what we have like to have this one, we measure what? We measure the P, and we also measure the deflection of this. Okay, and what we have from this is the shear diagram for this. This one going to be plus P over 2. This is minus P over 2. And also the moment diagram. Okay, and the maximum moment here, that's going to be under the load. It's going to be P. This is L over 2, right? P over 2 times L over 2. It's going to be PL over 4. Okay, and then when we test this, we interested in what? Interested in fractional modulus of elasticity. Okay, we will be talking about this later. We also consider the modulus of rupture. Modulus of rupture is the stress of failure. It's not the modulus, it's a stress of failure under fracture. That is usually for the brittle material. Okay, and we have also different type of this. Consider this one. We push the force here, and what happened is this force separate into this one and this one. If this is P, this is a P and a half, and this also P and a half. And then we have the reaction here and reaction here. Reaction going to be P and a half and P and a half. What we have here is the shear force diagram in the shape like this, and we also have the moment diagram in the shape like this, and our shear gonna be P over 2 and minus P over 2 here, and the moment, since this one is L over 3, L over 3 and L over 3, so the maximum moment going to be P over 2 times L over 3. That is PL over 6. And the good thing here is you can see in this portion there is no shear. So if you study the failure of the material due to the pure bending, this formation is good. Okay, but if not, the setting up of T-point loading is going to be easier. This kind of setting we call it 4-point loading test. Okay, this is another test. It's kind of a little bit harder to set up. So in the lab, we are only interested in the 3-point loading test. Okay. It should be noted that the bending test is usually used to find the tensile stress of brittle material. It's really useful to find tensile stress because the brittle material usually is hard to catch the specimen during the tension test. So it's better to catch it with clipping. You have the clipping problem at the end of specimen. So we use this fractural test for the brittle material. And like I mentioned, okay, this is 3-point and 4-point loading. And any kind of loading test, we have this equation to determine the fractional stress. Okay, and it's only used in the linear elastic. Okay, when you bend the specimen, okay, the upper part gonna be in compression, the lower part gonna be in tension. Okay, if you design the reinforced concrete beam, most of the time you put the steel in this tension part to taking care of the tension in the beam, and the stress that occur here is going to be compression on the top, and it's going to be tension on the bottom like this. And since this, the top going to be in contraction, the bottom is going to be elongation, and there is a point between top and bottom. It has no deformation. We call this is as the neutral plane. Okay, no contraction and no tension. The stress here is 0. And if you put it in the model, okay, the beam have the linear elastic behavior under the applied load. The strain gonna be have linear distribution like this, and also the stress gonna have the linear distribution like this. And then we have the equation that's compute the fractional stress sigma equal to m moment, okay, and y is the distance that you measure from the neutral axis up to the interesting point. And then you may see that since this one is large, so this one will have the maximum moment of m, and then c max over moment of inertia. So the compressive stress is going to be larger than the tensile stress for this section. And the moment of inertia, you know it, right? Because if you have the rectangular section like this, it have B and this is H, the moment of inertia about this I is going to be B H cubed over 12. You can compute it easily. Okay, and sigma max is going to be defined by that. And the strain can be computed by the stress-strain relationship. Okay, now what is the maximum stress for beam with brittle material? And we have linear elastic to failure. The beam is going to have the behavior like this. This is P, this is delta, and then it's going to have the behavior like this and fail here. So this is the linear elastic. Okay, modulus of rupture. Modulus of rupture is the stress of the failure of the material, can be computed by this equation. How we can get this equation? Is going to be sigma equal to m y over I. Okay, thinking about this, I equal to what? T times 2c cubed over 12. So it's going to be 2 power 3 is 8 t and c cubed by 12. So this is going to be 2 over 3 tc cubed. Okay, and the moment due to the T-point loading is going to be, we know that PL over 4. Okay, and then the Y you measure up, measure down for this is going to be equal to C. Okay, and then you divide it by this one, 2TC power T cube, 2TC power T or cube, and then it's going to times 3 here. So what we have is this cut, this is going to be 2. So we're going to have 3 PL, this is going to be 3 PL divided by 4 times 2 is 8 TC square. Okay, you got the fractural, you got the modulus of rupture by this equation. You can prove it easily, and many times in the examination I ask you to prove this step by step to get the equation that we can use to determine the modulus of rupture of the brittle material. Okay, it's very useful to determine the tensile strength of the brittle material. Okay, I also assign you to go back and review your static to draw the shear diagram and moment diagram of the 3-point loading and 4-point loading. And I should note that in this region of 4-point loading is important because it's the stage of pure bending, which is good if you prefer to study the behavior of the material only in the pure bending. That will be in accordance with the fractural theory. And then you're going to determine the fractional yielding strength. Okay, and as I mentioned, from this test you will get the graph of the load and the graph of the central deflection, and each graph represents the behavior of the steel. Okay, let us consider the first two, and the equation that's used to determine the modulus of rupture also used to determine the yield strength of the ductile material such as steel. Okay, this is the graph of the steel. We're going to use the 0.5% offset according to the ASTM. Okay, what it means is we're going to determine the 0.5 millimeter. This is in meter, and this is going to be 1 meter, 2 meter, 3 meter. So 0.5 is going to be here, and then you push, you draw the line parallel to the first part. That means this one you draw this line parallel to this one, and when it cut this point, you get the P offset, and then you put the P offset back into this equation. You determine the yielding stress of this material. And you also can check for the second one, but this time you got to draw the line that's parallel to the second graph, and see you get the P offset very close to the first one. Okay, but two graphs are a little bit different from to determine the E. Okay, next we also can determine the E. What the E? We can determine the modulus of elasticity of the material of the beam via test. What we have is, if we do the 3-point loading test, okay, under the application of the force, the beam will deflect, and we have the V max over here equal to PL cubed over 48 EI. And you can see this is what, this is the delta P, and this is the delta, and you may find the slope by delta P by delta theta. So by doing this, you may put P over V. You put the V down, okay, the P, and then you move 48 EI up, okay, this one up, and divided by L power 3. So actually the K can be related by this equation, and if you know K, we can determine the E. Okay, fractural modulus of elasticity of 3-point loading test can be determined by this. As I do before, you rearrange the equation like this, and then you get the K equal to 48 EI divided L cubed. Okay, by doing this, you got this equation. If you don't know it, you can open your textbook and find it easily, and then you get the K of this material of the beam easily. Okay, there are some limitations of the test results of static fractional tests. First, the deflection of the beam may not produce by the moment only. Okay, if the beam is the deep beam. What is the deep beam? Is have the ratio of L over D divided by 10. That means the beam have the shape like this. For example, is have the ratio of L. This one is the L, and this one is the D. Okay, this is less than 10. So when it's subjected to the force, what happened is there are some changing in the deformation here like this. There are some what so called shear deformation. Okay, when it have shear deformation, the deflection will include both bending and shear, and the result may not correct. So our beam to be considered must be long enough. And second, in determining the proportional stress of the beam, the top and bottom of surface of the beam subjected to maximum stress. That means for this, what is going to be on the top? The top going to be in tension, right? Okay, the bottom going to be in compression, something like this. Okay, it may have starting point of the yielding. Therefore, the yielding that start. Sorry, the proportional stress start at this proportion. Only the top and the bottom reach the proportion, but the inside won't. So the value that's computed by this fractional stress is just approximate value. Okay, because it won't occur at the same time, unlike for the tension. Okay, this is another picture showing you only some part has the yielding and the other won't. For the specimen, we gonna design the specimen clearly. First one, if we like to avoid shear failure maybe occur as a crack. Okay, at this portion of the beam, because under the force, this portion gonna have the V max. Okay, and that means to prevent from the crack at the end, you got to have the ratio of L over D between larger than 10 or 12. Usually we use it larger than 10, depending on the type of material, shape of structure, and applied force. Okay, and to avoid the buckling, if you bend the ruler, projector ruler, you can see the lateral buckling in the shape of this. If you have the beam, very thin beam, and you bend it, okay, you're going to get the beam with some kind of this so-called lateral buckling in the form of this like bull-like. Okay, to prevent it, you're going to have the ratio of D over B larger than 15. So that means your specimen supposed to be thick enough. Okay. For the testing machine and testing procedure, we have 3 types of fractural tests in our study. We also do the fractural test of the brick. Okay, sometimes brick also subjected to bending. For example, the wind, when it's subject to the wall, when the wall subjected to wind, okay, the brick also in fracture. And we have the lab number 8. On lab number 8, we do the fractural testing of the wood. Okay, we also do the long wood and short wood. Long wood usually fail by Mmax, and short wood may fail by Vmax. And also we do the fractural tests of steel. Okay, fractural step of steel is going to produce the yielding. Okay, or is called plastic hinge. And for the cast iron, the beam gonna fail abruptly for the cast iron. Okay, and when the test, you got to be careful when you test the cast iron. Okay, I recommend you to tight the cast iron specimen with the testing machine when is broken into two pieces, it won't fall down to hit your foot. And something should be noted on this. First one, during the test, we should notice and record the following: the type of specimen, the defect of the specimen is very important to defect specimen, the dimension of specimen, the loading of specimen, and some special type of failure of the specimen. Second, for the finding the fractural elastic modulus E, that's going to be defined from the slope K. Okay, the E that we have will be very close to the tension test and compression test. And let's note that this fractural test or bending test is very good for the brittle material, right? And the third, to obtain the proportional limit. This one may be a little bit larger than this one obtained from the tension test or compression test. As I mentioned before, since the distribution of the stress of the beam like this, so when it's reached the proportional limit or yielding, it won't reach that point simultaneously. So only part of it reach that stress. So that means we measure only that behavior, not the whole section. For the rupture is the failure of the brittle materials, such as when you put the concrete into fracture, concrete will crack easily. Okay, there is the research. Yes, crack easily. There is the research that we put like a glass fiber or the steel fiber to the concrete, so that will improve the tensile strength of the concrete. Okay, the failure of the concrete or the brittle material initiate at the micro crack in tension surface, and the crack expand rapidly due to the tensile strength of material until the beam cross section cannot take the load, and the failure occur immediately. Okay, and the failure of the timber beam, we also test the timber. There is different kind of failure of timber. The first one is of kind of a simple tension at the bottom, because this portion is in tension. Okay, this fail like this. This portion also in tension. This portion in tension. This is maybe due to the grain. Okay, have some kind of special grain direction, so the failure occur there, and the D like this. The compression also sometimes we observe it, but mostly we observe the tension. And the third, lateral deflection. We can prevent lateral deflection by putting a larger width section for the specimen. And the horizontal shear, this occur only for the short beam. We can design the experiment so that the beam fail by horizontal shear, and you can go to the book of Hippeler and find why the beam fail like this. Because of what? Because of the short beam going to have large V max equal to P over 2. So when it's subjected to the large force, the distribution of the shear stress is going to look like this. So the maximum occur at near the middle of the beam. So the crack occur here. Okay, going back to read the textbook about this, and the compression, and this is going to occur. This one, the fight occur due to the stress concentration of the applied force, and I will have an example to show you for this. Okay, this is the one that occur, but it's occur later than in tension. So this example have two kinds of failure. One is due to the clutching at the loading point, as I just circled the red one. But the other one occur like this. Which picture? It's going to be picture number 1, picture number C. Okay. And also, we found the crack at the end of this beam due to the shear stress. Okay, and we didn't find often. Each year I found is only one or two. Okay, and the top is a picture of our testing setup. We put the beam between the support, and then we put this. And I should mention that at the loading point, you got to put the steel plate here, okay, to distribute the force and prevent the failure over here. The yielding is a progressive failure of the specimen for the steel, for the aluminum, okay, is formed by the stress that occur on the section. When the stress, the maximum stress, reach the sigma sub y, okay, the stress start to produce the behavior of the hinge at the loading point, and you can see from the test the plastic moment, okay, will produce this kind of behavior, and the material at this section will behave plastically and form the hinge over here. And what happened later, that the deformation of the beam will increase rapidly under the small increment of the force. Okay, the factor that affect the fractional tests, there are many of them. The first one, loading type. Okay, for fractional test with the simple beam, you know simple beam, right? Simple beam is the beam that in the form of 3-point loading. Simple beam is going to be like this. The modulus of rupture, the failure stress is occur in the beam at the midspan. Yeah, sure, that's going to occur at this point. At this point, because it's going to have the maximum moment. It's going to be approximately 7% larger than that's calculate value from the rupture section. The fractional test for cantilever beam, you know cantilever beam, right? The cantilever beam is going to be the beam like this. We didn't test this in cantilever beam. I never. Okay, it's going to put the force here. What we have is the tensile strength. Tensile strength usually is the yielding stress is larger than obtained from the p-point loading. That is because of what? Because the failure of this occur at the support, and this is fixed. Okay, when this is fixed, it can take larger stress, so it's produced or the force that caused the failure of the cantilever is going to be larger than those from the T-point loading. Specimen dimension, big specimen dimension. When the span is shorter, what we have is from the fractional test of the concrete beam and from the cast iron beam. Okay, when the beam is shorter beam, the modulus of rupture going to get higher. That is noticed from the test. Okay, shape of the beam, we have the I section. I section show the higher failure load than the rectangular cross section. Okay, just use it for some notice. You may have a chance to test the I section or rectangular section when you work in the field. Okay. The size, larger side may have a lot of defect. Okay. So the fractional strength going to be decreased due to the larger side going to have more defect. Okay, more defect than the smaller section. Stability. Build up beam with the thin wall such as the I-beam, when you test it, okay, it's going to have some instability problem. But this one, okay, you have the lift of the wall of the thin like this, okay. When you push it, the top portion of the beam that is subject to compression may have some kind of warping here. There's some kind of that instability that occur due to the buckling of the thin plate. Okay, that is going to be in compression. For the wide flank beam, have the width to thickness ratio less than 15. That is going to be thin. Okay, thin wall section. This beam will got warping. This is the warping. I'm saying the warping of the section is a local flank warping. That is going to be occur in the compression zone. It won't occur in the tension because tension will try to elongate the flank. However, the compression going to contact the flank. When you contact the flank can warp it easily. And also they have a lateral buckling. Okay, before this the element stress here. Okay, after the application of the force, it may have the lateral buckling. That is going to have this one, this size wave. And also the combination of lateral and torsional buckling. That's mean what? That's mean before this you have the beam, okay, lay here under the force, and then your beam move laterally. This is gonna call laterally, and also is twist. It's twist. That means it's twist from the vertical like this. This called the torsion. This is twisting. And there are some kind of very thin web. For very thin web, you know web, right? Web is L. Okay, very thin web. If the web is very thin, under the force, web can be rippled like this. Okay, this kind of the beam for the airplane more than the kind of the beam for the civil engineer, and just make you the notice on this. And also this is what I did in the lab. I did some mistake because I didn't put the steel plate to distribute the force here, so it has some kind of stress concentration failure here, okay, due to very high concentrated load. Okay, and it's also causing the web to be warping like this, also due to this kind of local failure of the beam. Okay, the last one we're going to talking about the fatigue. In structure, if you have the bridge, you consider the bridge, right? What happened to the bridge? If you have the bridge usually subjected to what? To the vehicle load. And what the vehicle load? Vehicle load is a kind of moving load. Okay, moving load. When the bridge subjected to moving load, what happens is the bridge will deflect a lot when the truck come to the bridge. Oops, sorry. effect like this. Okay, it's going to be in tension on the bottom. Okay, and when the tug passes, it's just going back. Okay, what happened is the force that's applied to the bottom part of this start by 0, for example. Okay, and then when the tug comes, the stress just going up in tension and maximum. And then when the tug pass by, the stress just drop down to 0. So this happens every time when the tug pass. So that means the bridge is a kind of a structure that is subjected to life load that change inside that magnitude with respect to the time, or we call this one as the cyclic loading. There are many patterns of cyclic loading. This is going to be tension compression. This is going to be only in tension. And this is going to be a lot in tension and small in compression. So it depends on the type of structure you consider. Okay. And for fatigue, when the metal structure usually the ductile material, okay, it's gonna have progressive failure. But when it's subject with the stress less than yielding stress, that means it's still in the linear elastic. But when it's subjected to this stress for a continuous period of time, okay, the material just get fatigued and the failure occur as the abrupt failure. That is a kind of brittle failure due to the fatigue. This kind of important behavior that we need to be very careful on it. Okay, and especially when we design the steel bridge, or since the steel bridge also subjected to the cyclic loading. Okay, another one that's popular in the recent year is the wind turbine. The wind turbine also subjected to fatigue because it's going to have very large stress near this end of the turbine. Okay, and the force acting on it is the moving force due to the wind. So you got to be very careful on this. Some nomenclature that you should know about the fatigues. The first one is the mean stress. Mean stress is the mean average stress. So you just put the sigma max plus sigma mean divided by 2. And also this is sigma max, and this is sigma mean. Okay, and this is sigma max in tension, sigma mean in compression. So sigma mean is sigma max plus sigma mean divided by 2. So stress amplitude. The stress amplitude is the total length of the stress and divided by 2. So that is the amplitude. And the stress length is sigma max divided sigma mean. So the sigma amplitude is just the sigma length divided by 2. And if we consider some example, let's check out the wing of the airplane when it's maybe subjected to the wind during the flying. When we have sigma max of 10 and sigma min of -2, we can determine sigma m. Okay, the sigma m is going to be what? 10 plus -2 is going to be 8 divided by 4, so it's going to be 4 megapascal here. Okay, and if we like to determine the other, just stress amplitude. It's going to be what? Sigma max minus, let's say minus sigma min divided by 2. So it's going to, well, divided by 2 is 6 megapascal. And state length is going to be the total length of sigma max minus sigma min is 12 megapascal. Okay, and when we do the test in the lab, Okay, we will put the specimen. Put the specimen into the machine, and we put this portion into the motor to spin it up. And what we have is we're going to push the force up here, okay, and the force P gonna produce stress 1 if it's large, is small, let's say small, it's going to produce very small deformation like this, okay. And if you increase this to sigma 2, S2, S3, S4, okay, you're going to get the stress that's corresponding to P1, P2, PT, and P4. And if you spin this structural member by the test, the S1 may fail as N1. If this one is small, though, the S1 is going to be large, okay, is S1. That means if the stress is small, for example, if your stress is just like this, you're going to get 1 million. And if your stress is large, N is going to be small. That means if your stress is 700, your N is going to be, that is log scale. This is going to log scale. Okay, that is going to be like 300,000. Okay, and that is going to be the graph we call the SN curve. Okay, that's obtained from the fatigue test. Like I mentioned, it's the relationship between the stress amplitude with the N is cycle to failure. So we call it SN curve. S is the vertical axis, and N is going to be the horizontal axis. Okay, it's constant. And then the horizontal axis put in logarithmic scale. It's going to put in logarithmic scale. Okay, and then what we have is fatigue strength. Fatigue strength is the relationship between S and N. That is the stress that the material can resist from a given cyclic loading. Okay, cyclic loading. For example, if you like to have the material in the structure that can take 10 power 5, that is 100,000, so the stress is going to be 580. And if you like to take more cyclic loading, the stress reduce to like 460. Okay, and there is the stress that the structure can take without the failure. Okay, that is the endurance limit. Below this stress of 414, okay, the material can take the stress infinitely. And for some structure, like I said, it has the endurance limit, which is the stress below this material can have the infinite life it can take. And luckily, our steel, for example, that has the sigma sub u of 820, and you may have the endurance limit of 414. That is about half, okay, about half, or is a length of 0.5 to 0.6. Usually, the sigma sub e will be approximately 0.4 sigma sub u to 0.5 sigma sub u. In civil engineering, our steel, such as the Fe steel, we have what? We have the yielding of 2,400, and we determine the sigma allowable by divided by 2. So most of the time our allowable stress that's used to design the structure is 1,200 kilogram per square centimeter. And if we consider the endurance limits to be like 50% or 0.5 of sigma sub u. So the endurance limit of the steel can be 2000 kc. So our sigma allowable a lot lower than the endurance limit. So most of civil engineering structure, they won't fail by the endurance limit due to the coding specification that I just mentioned before. Okay, and however, you got to be very careful when you have the welding. When you weld the beam usually very long. Okay, it's maybe have a piece of 8 meter, and then you weld it with another 2 meter. And this welding, if the welder are very good, when they have the special way to cool the welding, that's going to make the welding to be homogeneous with the steel of the beam. But if the welder is bad, sometimes they just pour the water into this welding and cause the crack of the steel over here, and that is very prone to fatigue. Okay, so beware about quality of construction when we're talking about building the steel bridge by the welding. Okay, so most of the time our structural steel will not fail by fatigue due to the factor of safety of 2. Okay, and we have some non-ferrous metal such as the aluminum. The aluminum has no endurance limit. To do this, we got to set up Posidor endurance limit by taking the state value corresponding to some specific value that depend on the function and importance of the structure. Okay, you will set the band. If your structure can take very large number of cyclic load, for example, if your structure gonna take like this one maybe like a 8 times 10 power 7, so you decide this with the stress here, that's maybe about 160. If your structure gonna take like only a million cycle along its life, such as some part of the airplane, you can design it with a higher stress of 220. So it depends on you, depend on what you are going to use. The structure is subject to a lot of loading, so the stress is low. It is subject to limited number of cycle, so the stress can be higher. And by doing that, don't forget to inspect the structure frequently. Okay, the limitation of the test. In practice, the structure is not subjected to constant cyclic load as we use in the test. So when you use the testing result, okay, you need to be very careful, especially for small specimen. Okay, that's maybe inaccurate. Using the result must be very careful for the real world application. And the second, fatigue is not used in quality control tests. I mean, the steel company usually they do fatigue tests for the steel. So if we need to do, you got to do it by yourself. The testing machine and testing procedure, we have only one test for the laboratory machine. Okay, fatigue test of aluminum, and just take a look at this laboratory manual. It should be noted that the fatigue test to find endurance limit require a lot of number of tests, and it's going to be very expensive. Okay, the test is usually start with a high stress. So we will know the failure very quick. It's going to reduce, okay, times, okay, and we supposed to test to 3 to 5 specimen for a given state length. For example, if you test the specimen for very high 600 megapascal, you should test 3 to 5 specimen. And also, if you like to go down like a 500 megapascal, you still test 3 or 5. That means you're going to test a lot of specimen. Okay. The fatigue test panning, you got to consider the type of loading variation. Usually, the load is inside function, as one we have in our lab. The mean stress computed by this equation. Now, setting state in general first specimen set should be tested with maximum stress. Usually, it's going to be like 10% for the next. Let's see, if you have the specimen with the stress of sigma sub u of 400 megapascal, we may start by 360. Okay, and then the next one start 320 and 280 and 240, something like this, by 10% until you get the endurance limit, which usually is about half to 100. That means you're going to test is 1, 2, 3, 4, 5, and 6 set. Okay, 6 set of tests, and each set will contain about 3 to 5. That means if it's 5, you're going to test it for 30. If it's 3, you're going to test for 18. And the frequency of the test, the STM E466 set is going to be 170 Hertz. That is going to be 170 cycle per second. If you're going to test for 1.7 million times, so you're going to test it for 10,000 seconds, and that is going to test for what? 10,000 is going to be divided by 3,600 seconds per hour. So you will test about 2.78 hours. That means about 2.78 hours for each specimen. Okay, if you test like 3 specimen, you're going to spend a whole day testing this material. And okay, that is the end of second part of chapter 6. We study the characteristics of tests, and the first video clips we talking about the tension test and compression test, which are very important to our civil engineering work, because the tension test usually test for the steel, structural steel, the reinforcement steel, the pre-stressed steel, and the compression are important because we test for the concrete, we test for the brick, and then we move to the shear test. We didn't do much for the shear test because most of our structure, unlike in the mechanical engineering, didn't subject it to the torsion such as the shaft. And then we discuss about the bending. We have some structure that's subject to bending in our civil application, such as the beam. So it's kind of important also. And the last one for the fatigue test, that's kind of a special test. To be a special engineer, to be better than the other people, you got to know something special. Not much university in Thailand has a fatigue test like us at the SUT. So if you have that lab, I like you guys to enjoy it, learning it to make you special in some cases. Okay, that is the end of chapter 5. Hello, my student. We are going to talking about the mechanical property of materials for the chapter 6. And this is going to be the last chapter for our material testing. And following this, the main thing that you, as an engineer, you will encounter with the various material, which maybe include the structural steel, the concrete, the timber. Timber is the word for the wood, the brick, the aluminum, and the fiber reinforced plastic. Since you encounter many types of material and each material have their own characteristic, so you got to select the material properly in your analyze and design of the structure in order you to use it effectively. Before you can do that, you got to understand the mechanical property of each material. Okay, since they are different, as I mentioned before, that is going to be the learning objective of this chapter. And following this, after finish this course, you may have a chance and you may select the correct material for the structure. Let's you consider this tall building. This also called the high-rise building. Okay, high-rise building. And let's say if it's constructed, okay, in the middle part of Thailand, such as in Nakhon Ratchasima. Okay, if you are an engineer, what the material you are going to use? Okay, since in Nakhon Ratchasima, the soil are strong, unlike the one in Bangkok, that is the clay. We are in the location of the Petoa of Thailand, and our soil have strength. And most of the foundation that we use is the reinforced concrete with the lath foundation. Okay, and then when you construct it, you are going to use the steel at the structure or the reinforced concrete at the structure. You use one steel. You have the choice of reinforced concrete, or you may also have the choice of pre-stressed concrete. Nowadays, okay, the reinforced concrete usually can be used for the column of the structure. Okay, and reinforced concrete, you have the concrete, and you have you put the steel inside it. So the reinforced concrete is a composite material. That's combination between the steel and the concrete working together. And some column in a high-rise building not only have that rebar in the column, it's sometimes they put the steel, structural steel inside it. This also help the concrete to taking care of the force, and it can reduce the section of the column of the high-rise building. And for the slab, okay, for the slab, mostly in the high building they use the pre-stressed concrete slab, and most of the time you may hire large companies such as Siam Cement Group to do the slab design and do the pre-stressing of the rebar to make the pre-stressed concrete in the building. Okay, and then the facade of this building most of the time is built by the composite structure, such as in our intersection between University 1 Avenue and the 304 highway. We have a structure over there, and that's beautiful, very vibrant in colors. That's built by using the composite. The composite is mostly built by the aluminum. Okay, and if you have the aluminum structure. That aluminum will be very water resistant, and also is lightweight, high strength. And the wall in the building may be using the brick, especially in the area of structure that require soundproof. Okay. And also we have the modern materials such as the fiber reinforced plastic. I have my research in this when I doing my PhD in the US. They use this a lot. But after I come back to Thailand, I take this technology with me. But the acceptance of this FRP is very slow. Now we have graduate from HUT working on this. He is selling the what's so-called the Patut fiber reinforced plastic rebar. Okay, and you can search it by using the Google. This rebar is using instead of the steel rebar. Is very good in the area such as in the seashore or in the water treatment plant, in which the environment is very harsh for the steel. Okay, this is the example that you guys going to use this knowledge of mechanical property of the material in our civil engineering application. Okay, let us review the typical construction material that we are using. Structural steel. Structural steel can be have like a lava RB. Is maybe deformed bar DB. This is used in the reinforced concrete or the pre-stressed strand. That is used for the pre-stressed concrete, or it may have the structural section. We have the H, I, C, sometimes L, sometimes C. You have various sections. Second is a concrete. Okay, the concrete usually have the normal strength concrete. It's the normal concrete that is used in typical structure. And some high-rise building or special structure, we can use the high-strength concrete. Okay, usually it has the ultimate stress F pounds of C larger than 400 kc. Okay, and nowadays it's changed to 600 kc. Is up to the standard of each country. And in Thailand, you can order the ready-mix concrete with the strength up to 800 kc kilogram per square centimeter from SCG or from TPI or from the other company. And the third, these two materials are very popular in Thailand. And the third is a timber. Many years ago, 100 years ago, normal people build house by using the timber, and rich people build house by reinforced concrete. But nowadays, technology changed. Only rich people can build house by timber. I mean luxury house. Okay, because timber nowadays is very expensive. There is some kind of business in the US or in the western part of our globe, in Europe. They use the commercial forests. Okay, they plant the engineering wood, and they use the technology produce the engineering timber, such as the one that we study in the mechanics of material, like what's so-called a gulab. Okay, they put small piece of wood and attach together by special glue and some kind of curing that can produce small wood into the large wood. And the third is the brick. Okay, typically we have two types of brick. One is the clay brick. Okay, that is typical old style brick. Another one is concrete masonry unit. It's the concrete. That is the concrete. That is the brick unit. That's built by using the concrete here. And the fifth is aluminum. Okay, aluminum have anything you have can have structural aluminum in the high-rise buildings, such as in Hong Kong or Taiwan. They use the high-rise building with glasses for the facade of the building to let the light go to the building. That can save some energy. Okay, because the country over there in the summer, in the winter, is going to be very cold. So the sunlight can provide the light to the structure and provide the heat to the structure. And the cladding that support all this window made by the aluminum. Okay, that is going to call it structural aluminum. And there is another non-structural aluminum. You can see from the ceiling of the academic building one. That's all the ceiling is built by non-structural aluminum, and then they put like a plate of wood between the aluminum and then produce the ceiling of the roof. And the last one is a FRP. So it is your duty to select the material properly in the design and analysis of the structure. I show this picture to you to mention something about the construction industry lately. It's very, very prosperous in Asia. This first one is the Kingdom Tower. This is going to be the highest, tallest high-rise building in the world. It's going to be in Saudi Arabia. This is follow the high-rise building nowadays is tallest one is the Burj Khalifa. It's built in United Arab Emirates in Dubai. Since the Dubai is a small country and have the high-rise building, that's why Saudi Arabia said, I'm going to build another one that's taller than you. That's competition. Build the competitive environment in our civil engineering. And then there are a lot of high-rise buildings occur in this world. In Thailand, we have the superstructure. Okay, this is 615 meter height. It may not be the highest one in the world, but it's the highest one in Thailand. And also this structure has some kind of glasses facade, and build this one really beautiful, and it requires some application of the high strength steel and the high strength aluminum. Anyway, when you build a structure small or tall or big or very large, you're going to consider three things. Your material that you use in the building must have enough strength. Okay, won't produce any crack under the force, won't cause the yielding under the loading. Just strong enough. And the deflection of those material using to build the structural member is supposed to be very small. Large deformation cause the structure lost their function, and also sometimes cause very high vibration. So this building seems unsafe for the people. And the last one, the structure supposed to long lasting, supposed to very durable under the weathering from the rain, under the action of the wind. Okay, that is very important for you to consider the material. So what kind of question you should ask when you are selecting the proper material? The first one, what type of material that are available in the market? For example, if you like to use the concrete with the strength of 1200 kc, That's going to be very expensive because it's very rare to use that very high strength concrete. Okay, and in Thailand, mostly you have two choices to build the structure. One is the steel and one is the concrete. Okay, and the concrete can be RC or can be PC. And what else do you use for this? The mechanical property. Okay, you're supposed to compare them. The steel is kind of ductile material. The concrete is kind of brittle material. And then you reinforce the concrete with the steel. So you produce a composite structure that's appropriate, more ductile. And then compared to the strength, the steel have higher strength and higher stiffness when compared to the concrete. But anyway, the steel are susceptibility or less durable for the weathering than the concrete. When it's wet by the water, it can get rust easily. So the steel, you need to have the rust-proof material to paint it. And sometimes you also need to spray the fireproof material into the steel. Unlike the concrete, okay, concrete won't rust. Concrete is also very durable to the fire. Next, how the maintenance, like I mentioned, the concrete has very high performance for maintenance. Steel require a lot of maintenance compared to the concrete. Needs fire protection and rust protection, but concrete won't. That's why when we doing reinforced concrete and the pre-stressed concrete, very popular in Thailand because they use both of the advantage of these two materials. When they work together, they help each other more and more. Next, the cost of it. This is hard to compare between the cost of concrete and the cost of the steel. But in Thailand, the reinforced concrete and the pre-stressed concrete are more popular because the weathering in Thailand and the experience. The Thai engineer have a lot of experience with the reinforced concrete and pre-stressed concrete more than the steel structure. Most of the steel structure used in industrial building, okay, like the plants, Honda plant, Toyota plant, those kind of large plant, they always built by the steel. Nowadays, there are some company that trying to use the steel in the buildings such as Siam Yamamoto Steel. That I also sent some of information to you already. And what else? How to use this method in the construction. It's about the construction management. Okay, in the past, when you use the steel can be fabricated in the industry. You can cut and then you can drill it and then you can ship it or transportation it to the construction sites. And that's going to be very convenient. And the structure going to be in high quality. Okay, but nowadays the concrete also have some kind of precast, okay, concrete. Okay, it can produce as the concrete plant. Okay, in the concrete plant. So this pre-stressed concrete can be both RC pre-stressed and the PC pre-stressed, going to be high quality also. But the weight of it may be large during the transportation compared to steel. And the installation also harder compared to the steel because the weight of it is a lot. Okay. And how do you spec the material in your contract? That means you got to say for the concrete must follow the Thai industrial standard number year. The same thing, if you spec follow the international standard, you may use the British standard, you may use the American Society for Testing and Material or STM standard. So this is the first thing, okay, that you gonna study for each material, and then you got to push it into the contact. So when the people bidding for the construction of that structure, the contractor must follow this contact, must follow the specification that you as the engineer write it. Okay, and if not, sometimes it's not only the legal problem you may have also suing those kind of things, and you got to pay back if you didn't follow what you are going to work within the contract you have. And the last one, if you have specification, you got to test it. For example, if you use the FE24 steel following the Thai Industrial Standard 119, and then you buy your steel for like every 10 tons, you got to correct at least 3 to 5 specimens and send it to the lab. That 10 ton of steel, that's cost 300,000 baht. That's quite a lot of money, right? So when you buy things, you got to have the test for the acceptance quality control. That means you are going to use the knowledge of this equation. Actually, most of the time you didn't test it by yourself, but when you get the result from the lab, you can compare with the spec, and then you can decide whether you should accept the material or not. Okay, let's consider this structure that is in Phetburi near Lam Pak Bia. That is the King project. Okay, they trying to restore the forest, the mangrove in the area of Phetburi, and they have the structure that's for the traveler to have a chance to take a look at the mangrove forest. And you can see this bridge made by what? This bridge made by timber. Okay, why don't they use steel in this area? And this also concrete, the RC column. Okay, they use the steel here because the steel is susceptible to the seawater. It can get less. And if you use the RC column, it's going to be a very special design on this. Okay, such as you put the steel inside it. The covering of this is going to be 3 inches. This is going to be 3 inches or 7.5 centimeter or 75 millimeter. Unlike the column that you use in the typical building. Okay, especially the one that's inside the building. The covering here is only 25 millimeter. That means the covering is going to be 3 times larger to prevent the seawater attack the steel in the column. Okay, for the wood, it can take the seawater without corrosion. Okay, let's start about the structural steel. Nowadays, like I said, they are trying to use the steel more and more due to the steel has the high strength to weight ratio, and the steel industry going up very quick in Thailand. In Thailand, we have many companies such as Bang Sapan Milwa, that is in Prachuap Khiri Khan. Also, Saviya Steel Industry, that's also in Prachuap Khiri Khan. Or Siam Yamato Steel, that's in Sratburi. There are many steel companies in Thailand, as they are big also. they are going to produce the product that follow the Thai industrial standard. And like I said, Dual-methylene can come to this industry? No, it's not. It's very hard because this company is big. Okay, most of the time in Thailand we don't have the steel. We got to import the iron ore. Okay, we don't have iron ore in Thailand. We bought the pig iron, which is the iron ore that's only passing manufacturing process. And this pig iron is going to burn and adjust some percent of carbon. And then we produce some type of structural steel. Okay, and we have many grades of them. Okay, this is the pictures of manufacturing of the steel product. It start with this one occur usually in some country such as in the China or Brazil or Russia, and then this going to produce to be like a pig iron. When it comes to Thailand, okay, this pig iron may put into the arch furnace. Okay, sometimes we also have recycled steel and put in the arch furnace. And then there is some special manufacturing process, and they cast the liquid steel, okay, into the slab, thin slab, those kind of things. Okay, that is we have. This is occur in another process. Okay, that is usually we don't have this startup of the steel, but the pig iron can go there. And then the steel may have many types. For example, if you're talking about this beam, okay, the section may be something like this. If we're talking about the purlin here, the section can be the C, and this C, this is Z in Thailand, or C here, because we can connect, okay, the section into the beam of the frame easily, and also we can connect the metal sheet into this purlin or into this beam easily also. Okay, and the construction steel. Typically, we have three types of them, and the first one is the wrought iron. We don't use much wrought iron in the structure, but the wrought steel is used, okay, in the window. My window house also have the wrought iron to protect, okay, the lobster into my house. We use it a lot in Thailand because it can bend easily, and it can subject it to repeated load. So most of the window in Thailand have the bent steel to protect the house. And we use of steel. Steel can be two things. It can be carbon steel, and it can be the alloy steel. For the carbon steel, the main property of the steel is based on the percent of carbon that put into the steel. When you put more carbon into the steel will improve the strength, improve the hardness, and reduce the ductility. That means high carbon steel sometimes have high strength and high surface and less ductility. And if the property of the steel depend on some additive such as silicon, nickel, magnesium, chromium, those kind of things, we call that steel is alloy, such as the stainless steel. Okay, I have a student who work by putting the stainless steel at the reinforcement of the concrete. The stainless steel is good because it can withstand to the weathering from the seawater, from the water, it won't get less, but it costs 3 times more expensive than typical steel. Okay, that is sometimes you going to use this alloy steel, especially if you work in the southern part of Thailand. Okay, this is different steel. Is for the steel with a carbon of 0.11. When you increase the strength of the when you increase the percent of carbon to 0.32 to 0.62, you can see the stress strain curve going up. The strength going get higher and higher when you put you increase in the percent carbon. And also the heat treatment also increase. So the steel property not only depend on the percent carbon, it's also depend on the manufacturing process also. How? Because when you treat the steel with the heat, you heat it up again, and then you control it for cooling step by step. So the grain of the steel gonna get smaller and very smooth. Okay, close to the theory. That's why it's improved the strength by heat treatment of the steel. And the last one that we have is the cast iron. For the cast iron, we put a lot of carbon into the steel. That's going to increase the compressive strength of the material and the surface hardness. This is important in some applications such as the train rail. Okay, since the wheel of the train also the steel, so the train rail must be the steel, and it must be hardened. When the train breaks, the force from the train won't hurt the surface of the rail. Okay, and since the rail put the force on the since the train put the force on the rail as in compression, so cast iron is very good for the railway track or the train track. However, since you put the carbon into the steel with high percentage, that carbon cause the micro crack between the steel and the carbon. And then when you pull it, what happened is the micro crack open and it's gonna fail in tension quickly, and it's going to have low tensile strength with the brittle failure. Unlike in compression, under compression, micro crack close to each other, and it also have the boson effect. So the cast iron can take a lot of compression. Okay, this table shows you the typical and usage of the steel. Mostly follow the ASTM standard. Okay, we use the mild steel, and for Thai TIS, you may use specified by FE24, okay, or FE30. That is going to be the typical mild steel that we use in Thailand. So anyway, when you decide it, you got to take its mechanical property and follow it closely. There is special steel that's used in some mechanical engineering industry, such as in automotive industry, for the spring, and for some car they use some kind of special steel, such as this one, the medium strength, and that's going to use in many industry also. So in short, when you put the carbon into the steel, the strength going up, hardness going up, ductility going down. You put the alloy in it, it's going to improve some required mechanical property, such as if you put silicon, you increase the strength. Okay, if you put the copper, you got the higher corrosion resistance. if you put the manganese into it, you improve its hardness. Okay, so mostly the property of alloy steel bases on what additive you put it in. Steel have the property of behavior of elastic and plastic behavior. During elastic, that we have mostly we use this as the sigma sub y. The property over here is elastic. That means if you pull the steel and still have 2 centimeter elongation and you release the force, the steel gonna contact to its original length. For example, 1 meter, you pull it to 102 and you release the force, it just go back to 100 centimeter. That means the steel is in elastic behavior. But for example, if you have steel 1 meter and then you pull it passing this elastic region and go to the plastic region, for example 1 meter steel, okay, if you put it small, okay, you got it 1.02 meter, that's in the elastic behavior, right? But if you pull it to 1.10 meter, it's going to come to the plastic region. And when you release the force, it won't go down back here. It will come back, okay, following its original linear behavior like this. So by doing this is going to have some what's so-called the elastic recovery, and some going to produce the permanent set. Okay, if you consider what we have in our examination, we also talking about this kind of behavior also. And now what it have is the behavior of this material chain. Usually it has the elastic region up into the last boot, and now it gets larger to this blue line. That means the elastic region get larger and you also get the higher yielding. So this time you may use the sigma sub y change to here. That is good, right? Yes, it's good, but it also has the drawback. Usually it can elongate following this less line, but this one is going to change to reduce to the orange line. So your material is going to get more brittle, okay, and then the energy absorption of this material also less, since the area under the stress strain diagram reduce. Okay, now after we consider the diagram for the steel production, and then we get the steel plate, and now there is 2 more steel production process that's required. One is the hot working process, another one is going to be cold working process. In the hot working process, the steel that we have from the previous slide will come to the reheat furnace, and then it have some kind of manufacturing process to make it like a pipe, okay, to make it like a commute, those kind of thing. It depends on what the process you have. Okay, some going to produce the structural mill and some produce the bar and the rod. Okay, most of the time they have 2 things, the slab going this way and the boom and bullet going to be this way. Most of the Siam Yamato cement, Siam Yamato steel or the BSBM, Bang Sapan bar mill, or Savia SVI, they can produce the structural section and the bar section. And hot loading process, okay, after you reheat it and then you try to control how it's cool, you make the steel more strength and more toughness. by reducing the residual strength and get the finer steel grain, and then you can load it. When you load it, that means you're going to get this one, the structural mill. Okay, you load it, you got the section that's similar to this, like beam. This is for the I or the H or the W section, column, channel, ankle. Okay, this is usually for the purlin or the small structure, and this may be used for the truss. This may be used for the truss member or the column, okay, or the beam. Okay, this more maybe you use for the small structure like the purlin or maybe some kind of ceiling structure. That's going to follow the Thai Industrial Standard 1227-2549. And for some other country, you got to check what standards they are using. And next, for the whole working process, most of the time this is going to involve with the steel plate. Okay, they put the steel plate into the some process which cause the stain hardening. This will increase the strength of the steel, the surface hardness, but the same as you know, the toughness is reduced. Energy absorption also reduced. This is usually used for colorless section used in a minor structural member. Okay, and then the process produced is called cold rolling. It's cold rolling, not low when it's hot. It's low when it's cold. Okay, and then this must follow the TS 1228. Okay, next, the steel that's used in the construction mainly separate into structural steel, like I said, from the production. Okay, and when it's hot low, you may get the W section, which is the H section. This is American, this is Japan, or the I going to be like this. Okay, W and H gonna have equal to the width and the depth, but for the I, the width is smaller than the depth. This is the I. Okay, sometimes you may have some other section such as the T, such as the L, such as the C. That is going to be the structural steel. For the reinforcing steel or rebar, we have this is the RB, and another one we have this kind of thing to increase the bond between the steel and the concrete. We call it deform bar. RB usually used for the stirrup. Okay, sorry for the STI. STIRRUP, and the DB usually used for the main reinforcement. The reinforcement. Okay, this is going to be the not clear yet. The main reinforcement is supposed to be in a beam like this, on the beam on the top and on the bottom. For the stirrup, usually it's going to be this one, but this is not clear. This is a big beam. Let's use the DB as a stirrup. So structural steel is going to produce in that section because the section, as I show you, has the high IOA ratio. Example, if you have the steel with this is 3 centimeter and this is 10 centimeter, this is going to have 30. Okay, 30. This is 3 centimeter and 10 centimeter. This is going to have 30 centimeter square. And then you use this one and you produce the section with the plate of this one is 10 centimeter. This is 1 centimeter, and the same 10 centimeter, 1 centimeter. This is going to use the same area of the steel. The moment of inertia of this, let's say this is going to be I1. This is going to be 10 power 3 divided by 12. Okay, you may get this for what? 3000 divided by 12, and that is going to be centimeter powerful. However, the I here, you may have this one for what? For, let's say this one 1, and then this is going to be 10. This is 10 power 3 divided by 12. Okay, and do plus 2 times of this one. This is going to be 10 times 1 power 3 divided by 12, plus the area here is 10 times 1, and it's going to times this one square. This is going to be 10.5 square. And you can see that this is I2. I2 is a lot larger than I1. So that means this kind of structural section has higher moment of inertia over area ratio. So this material, this section is going to be very effective. Okay, very good to build this kind of special structure. And you got to call them. Okay, it's just called by its section. W is wide flank. It's going to have this kind of section. And this for the I, this S is the American standard, but actually we can have the I section, something like this. This is I section. C is going to be this section. Okay, and then L. Okay, L have both unequal leg and equal leg. And then the symbol here is will follow by the depth, the depth of the section. And the last one is going to be weight per meter of this section. So you got to call them correctly to get a proper section. The method testing of structural steel, you got to follow what we have for the dimension and weight. You got to follow this, depend on the steel that you are using for the hot rolling, for the cold rolling, and for the strength and the elongation. Actually, you also can follow the TIS 119, I think it's going to be correct, or the E8. Okay, 119 is going to be FE24, E8 maybe A36 still. And you don't cut 3 specimen, and the cut you should not use heat. You got to do it mechanical cut, and each of them going to be 1 to 1.5 meter, and each the plate. Okay, the width supposed to be less than S times the thickness, not too much width. Okay, and the detail of this you can do it when you go to work. Okay, for the TAS 55, that is for flat and square steel bar. Okay, you got to follow this. They will ask you for the yielding, ultimate, and percent elongation, and don't forget about the E. Okay, if this is 2400 kc, 235 megapascal in SI, the E is going to be 200,000 kc, or it's about 200 gigapascal approximately. And if you have the hollow section, you're gonna follow the TAS 107. Hollow section has a symbol of hollow H, and S is section, and then it's spec by 41. That is spec by ultimate stress, not the typical yielding stress. And if you go to the structural section, that's hot loading, cold loading, you get of FE24. This 24 going to specify your yielding stress. This is follow the Thai industrial standard TAS, and you may see Our unit is kilogram per square centimeter, so you got to beware on that. Now we come to the reinforcing steel. You know this one. This is for the reinforced concrete. Okay, we put the steel in a proper manner, following the design that we specified it. Okay, and then we put the formwork to cover it, and then we pour the concrete. And when the concrete hardened, the concrete will cover the steel, and they're going to work together as a composite material. We put the steel into it because that's going to help the concrete to resist the tension force, because the concrete have very low tensile strength. It's about 10 to 15% of the composite strength. Another one is concrete also can help to reduce the creeps. Okay, the creep. For example, if you have the cantilever like this, and since the concrete, they have not only the concrete have the sand and the crushed stone inside it, and it have the air void. Okay, air void. And in the air void, they have water in it. And when it's subjected to the force, okay, this part going to be in compression, and then the water gonna to leach out from the air void. And what follow is when the water out, so this beam may defect like this. Okay, and when the force release, it won't go back, it won't rebound back due to the creep. One of the thing is you got to put the steel into this portion in the proper amount. Okay, the steel will help the concrete to taking care of the leach out of the water, and the creep can be reduced. The same thing as for the reduce the width of the crack. We have the temperature steel. That's produce the crack due to the change in the temperature of the slab. The reinforced steel is a mild steel. Usually they have very low carbon. Okay, and you can see each kilogram may cost you 30 baht. And then if you buy it for like a 10 ton or 20 ton, that's going to cost you 500,000 baht. So you got to be really careful when you check the steel. When you check the steel, you may have the symbol like this. This RB is follow the round bar. This 25 is going to tell you about the diameter. Okay, and this is going to be the trademark of this, of the steel. This is going to be some kind of company. And then the grade of the company of this is SR. S is steel, R is the round. Okay, and then it's only have one grade of 24 for this round bar, and you got to check it. And we also have some kind of deform bar. The picture show his deform bar. We have deform bar because we have this to increase the bond between the concrete and the steel. And the steel must be very ductility. It must be bent like this. We got to bend the steel because we're going to increase the bond again between the concrete and the steel. Okay, the first one, the round bar, as I mentioned, is RB. Okay, RB is RB. Depend on the size. This is RB6. This is 6 millimeter. If it's 28 millimeter, it's going to be RB28. And it has only one gauge of SR24. The tensile strength must be larger than 2,400. Okay, in the standard that's goes by, they're going to sell us for 10 meter length. We cannot longer than that because it's hard to put into the truck or put into the tin wheeler. Okay, you got to take this. And then what we have is the table of this round bar. Okay, you got to check the diameter when you send it. There's going to be some allowable for this. You got to check the weight of it. Okay, and this Lao bar must follow the TAS 20. Okay, TAS 20. The Lao bar must be have the smooth surface without crack. Then cross section must be round and uniformly along its length. And you can have two ways to determine the diameter. You may use vernier as you did in the lab. Okay, putting in 3 points and do the average. Or you may weight it and then put into this equation. And the discrepancy is this. Okay, it cannot be larger than this. However, even though it's within the discrepancy, what happens is when you test its mechanical property, it cannot less than specify sigma sub y, sigma sub u, percent, elongation, and e. For the mechanical test, you got to follow this. Okay, and then when you get the result, just compare it with this value. If one of them cannot pass this, you got to reject that material. Take it out from your construction sites and bring in the new one. Okay, and the bend test is like this. This is showing the bend test. When it's bend test, we should not have crack around here. We bend it because we try to increase the bond between the concrete and the steel. The deform bar have the lips, okay, on the surface, and the lip must be designed properly as specified here. Okay, and the detail you can read it by yourself. The deform bar have the symbol of dB, and it said it's dB10. That is the deform bar with a diameter of 10 millimeter. If it's D bar 20, that's going to have diameter of 20 millimeter. Okay, the diameter is important because the spacing between the rebar, okay, must be larger than 3D spacing, because to reduce the stress concentration, something like that. So the size of spacing is important. And this is the table for the size and the weight. Okay, and you may say you have this size, and then you got to check what you have for your cross section, and you must follow it. And again, the rebar gonna have the dB here, and also the size here. Okay, this is a company that produces, and this is the grade. Okay, this is the grade of this. It's maybe SD30. Now it's have a SD40. It have a SD30. That's old standard. And now popular is SD40. And the new one is going to be SD50. They are going to develop the strength of the steel in the way that they like to use it less. Okay, to make this structure more and more effective. Okay, so your new engineer, check it out for the SD50. The TIS that you must follow is TS 24, and they have a detail. You got to follow the test like this. And I didn't mention this much because you're going to use this when you need, and then you know where you should find it, and just come and check it out. SD30 is set the yielding at least 3000. SD40 the yielding stress at least 4000, and it's going to follow the ultimate the percent elongation like this. If one of this property won't pass, you got to reject it. Okay, you should not accept it. Okay, next we're going to check the size. The rebar is hard to check the size because the deform bar have the lip. Okay, so you have only one way to check the size of the deform bar by putting into this equation. You got to weight it. You got to measure the length, and you put it into equation. You get the diameter. The standard of test, there are a lot of standard of tests. The important one is for the reinforcing steel. This is for the RC. This is for the RC. This is for reinforced concrete. For the pre-stressed wire, this is for the pre-stressed concrete. A lot of building is using this. You go by TS425. For structural steel, the section of like I, C, T, okay, you got to follow this. This is hot loading. This is cold loading, structural steel. And for the STM, they also have many kind of them. I just put them together here as the reference for you in the future. And what the advantage and disadvantage of using the steel in construction? The advantage, steel have the high strength to weight ratio, so it can be used in the high-rise building and long span structure. For example, this bridge, okay, the span here is very large. If you put this into the concrete, you may see this is going to be different type of the thing. And if you build it in the rough area, in the mountain area, it's hard to transport the concrete into the construction site. So the steel is better to fabricate in the steel plant and put them into some 10-wheeler, some truck, okay, semi-trailer, and move it into the mountainous area. Or even you use the helicopter to deliver it, okay. And the property of the steel is very uniform because most of the time it's built in the industrial environment. Unlike the concrete, you may put it, and when you pour the concrete, the rain may come, and then the property of the concrete may be degraded due to the rain. It has high elasticity. It can very elastic, okay, and it can be have the long lifespan if you maintenance it properly. There are a lot of steel bridge in the US. They have a lot of buildings because in the US, the steel industry is very popular, and some of them may have 40 or 50 years old. Okay, that means you got to maintenance is follow the proper schedule. And it has high ductility and toughness. It can be used for guardrail when the car hit it. Okay, this one won't break, and it can hold the car within the traffic area and won't fall down into the mountain, something like that. And the last one, it is of construction. As I said, it can be pre-built and put it into the truck, ship into the construction site, and put them into the position. Disadvantage, high maintenance, that we talking about before, is have both fire and rust. Okay, you got to put the fire protection. Okay, that's going to reduce the heat that's transferred in the steel. And the buckling is a problem. You can study from the chapter 13 of the mechanics of material, okay, about the buckling material. Okay, you got to check the steel have enough bracing or not. Even though it is too slender, you just put some bracing into the steel. When you brace it, the buckling strength, okay, if you brace at the half of its length, the buckling strength can improve for 4 times. You go back to that chapter, you can see it. It's going to have the problem fatigue, but actually it's not directly due to the fatigue. It depends on the welding. Okay, as I mentioned, usually is have the sigma sub u of, let's say, 4000 kc, and the endurance limit sigma sub e half of this. That is going to be like a 2000 kc, and sigma allowed that we use usually is going to be 2500 divided by 2. That is going to be about 1200 kc. So most of the time, the allowable that we use in the steel design is less than the endurance limit of the steel for the fatigue. So fatigue won't have the problem with the steel bridge, won't have the fatigue problem, but the welding, okay, on the steel have some problem if the welding is not treated properly, such as when the welder finish the welding, they just pour the water into the weld, and that's going to cause the crack in the steel, and it's really prone to fatigue. And written fracture at very low temperature. This is important if you're going to work in the northern pole, in the area very cold, or in the frozen room, okay, in Thailand. Okay, that's what we have for the first part of the steel, and you're going to have some knowledge of the steel, both the structural steel and the reinforcement steel, and you supposed to specify the steel properly, follow the Thai industrial standard if you work in Thailand, or your country standard. And when you put the specification in the contract, you got to follow that. When the steel shipped into your site, you got to collect some specimen and send it into the university or approved laboratory to get the result, and you compare those results with the one in the contract. If it won't pass what you spec in the contract, just reject that and ask them to bring the new one. Okay, that is important to us. Okay, that is the end of this part.